Hello, my name is Tafik Suleiman, and for my ECE 470 extra credit assignment, I'll be discussing one of my favorite topics in the class, robot control. Alright, before we jump into robot control, what is a robot? Simply put, a robot is just a machine designed to accomplish a task by carrying out a complex series of actions automatically. Robots can be guided by an external control device, so the control may be embedded within. Robots may be constructed on the lines of human form, but most robots are machines designed to perform a task with no regard to the aesthetics. What are some types of robots? We got mobile robots like automated guided vehicles, industrial robots such as the arms you see at manufacturing plants, educational assistant robots like the Lego Storm robot kit that you probably played around with as a kid, and so much more. Now, robots have existed since ancient civilizations, but only really started to take form with industrial applications and slowly evolved by incorporating artificial intelligence or more complicated programming algorithms as well as better sensors. And that has led to what we now see for household applications like Roombas that vacuum carpet floors, and industrial applications like the robotics you see at Tesla's manufacturing plants. How does a robot work? A robot can be broken down into three simple parts: the sensors that take inputs from the real world as data or variables, passes that information to the controller that makes decisions based off that input and uses that for processing different calculations and things like that, as well as the end effectors, which form some form of output or interaction with the real world or produce some output. In this video, we'll be focusing on robot control. What is robot control? Robot control is a study and practice of controlling robots. Every robot has some form of control or controller in it that interacts with the sensor input component, processes that data in complex and various ways, then updates the end effectors or output components to perform desired results or provide some feedback. The robot is programmed with set commands or can have update commands that uses or references input from sensors that observe the environment and provide feedback to the controller as input. These sensors could be cameras for visual input, gyroscope for orientation position input, IR and LiDAR sensors for depth perception and input. The controller is the brain component that takes that input and commands and processes those to make decisions, that uses the input to meet those commands if possible. Once the decision or action has been decided upon, the controller sends commands and decisions to the end effectors or actuators as signals to perform that desired action or feedback. In most cases, robots are designed to continuously do this in a continuous or limited loop where it updates the input as it may change or may be affected by the last robot's state or actions. This is called the feedback loop. Ideally, the input would be always accurate, but due to real-world situations, these inputs are almost never perfect, are usually incorrect, and or need to be adjusted for the desired action or decision. As part of the feedback loop, this process is called estimation, which is usually programmed into the robot based off of testing and calculations. A great way to explain robot control is through autonomous self-driving vehicles and their various control theories. Various forms of controls are bang control, where you immediately adjust effector output as soon as the input changes, which is not suitable for various real-world applications. There is also proportional control, which is the above, where the effectors adjust based off the size of the value or value change using a variable called the proportional term. Error control is the next step above that, where you take the error of the input and scale the output proportionally by the error using a constant called proportional gain. This improves it but increases the chance of the system going out of control and doesn't account for overshoot. The next step above that is to include more error correction variables in your estimation equation, such as by adding an error rate variable or derivative term to smooth out that overshoot. Then adding this to the proportional term hence improves it much further. This equation is still not fully satisfactory, hence the next step above that is the full equation of PID control, meaning proportional, integral, and derivative control, which is a generally used control model but still faces its own issues. This is accumulation of adding the proportional term, the integral term, and the derivative term to solve most of those issues in the earlier control models, but it still faces its own issues. Robotics applies many more advanced control theories based off or similar to PID control, and that allows us to use robots much more efficiently. Now, to wrap up this video, I'd like to end it with this quote by Neil deGrasse Tyson. With regards to robots, in the early days of robots, people said, oh, let's build a robot, and what's the first thought? You make a robot look like a human and do human things. So 1950s, we're so past that. As you can see, robot control and theory has evolved throughout the days, and to end this video, I'd like to reference you to this funny video of Will Smith flirting with the AI robot called Sophia. Thank you.